Happy World Carnivorous Plant Day. My name is Dr. Lindsay Pett, and today I'm excited to talk to you all about a small experiment I conducted on Metronemus nabi, or the pitcher plant midge larvae, determining whether this larvae is actually capable of emigration when faced with unsuitable habitat, specifically in the form of pitcher desiccation. Now, the first thing I wanted to mention in this presentation is the actual habitat for Metronemus nabi, which is Sarracenia purpurea, or the northern pitcher plant. Purpurea is a long-lived carnivorous perennial herb that contains an entire aquatic ecosystem within its pitcher-shaped leaves. And the ecosystem that resides within Purpurea actually contains numerous obligate organisms and complex trophic dynamics, which you can see here. And I wanted to briefly review the organisms that make up this aquatic ecosystem that resides within Purpurea. So this includes a top predator who is an obligate flesh fly larvae, Fletcheri, that will shred prey when it enters the pitchers, followed up by Metronemus nabi, or our obligate pitcher plant midge larvae, that breaks down prey as well as consumes detrital matter. We also have a host of bacterial species that aids in the decomposition process, which in turn is consumed by plankton, protozoans, obligate aquatic mites, and an obligate omnivorous filter-feeding mosquito larvae, Smithii. Besides consuming bacteria, Smithii will also consume plankton species, our obligate mite Gibsoni, as well as protozoans. And if we go back to the top predator of our food chain, Fletcheri, not only is it shredding the prey that enter the system, but it's also consuming Smithii and in some instances being cannibalistic. So there really are complex trophic dynamics occurring within this microaquatic ecosystem inside of Purpurea's pitcher-shaped leaves. And I actually used this complex ecosystem for my dissertation research, studying aquatic ecosystem stoichiometry and ecosystem processing. And a major portion of my dissertation research involved sampling Purpurea up the East Coast from Florida to Maine. And as I was sampling these plants, I noticed that at a majority of the sites, 18 out of 28, there was major damage to the plants in the form of herbivory, which you can see here. Now, what's obvious from these pictures is that there's a loss of plant tissue, but what might not be obvious is that there's also a loss of pitcher fluid. These plants were becoming completely desiccated. Now, after observing all of this damage, I thought, well, who's the herbivore that's consuming so many plants? The extent was really extreme. There were some bogs that had hundreds, if not thousands, of plants, and I could maybe sample from a handful of them because the rest just did not contain any fluid. And after doing some research, I actually determined that the organism causing all of this damage is an obligate herbivore of Sarracenia purpurea, and that is the Xyrophax, or pitcher mining moth, which has a range from Newfoundland all the way down to Florida's Panhandle. Now, I wanted to briefly go over the life cycle of the Xyrophax moth larvae and how it eventually causes pitcher desiccation. So here's just a cartoon version of our female Xyrophax moth looking for a suitable pitcher to lay her eggs. She will normally select the largest pitcher she can find and land. From there, she will go into the pitcher through the pitcher opening, where she will lay approximately 3 to 5 eggs on the interior lip of the pitcher. Our adult female will then leave her eggs, and in approximately 12 days, our eggs will hatch into larvae. From there, our larvae will begin to feed on the interior plant tissue, from right above the pitcher fluid to the pitcher opening, which the larvae have also enclosed with a silken web. This web will keep predators away from the larvae, but will also prevent Purpurea from receiving nutrients from prey that would normally enter the pitcher. Now, these larvae are really good at consuming plant tissue, and after consuming the plant tissue they were originally laid in as eggs, they will leave through the pitcher opening and go find a new pristine pitcher in which they will enter and start consuming that interior plant tissue as well. And these larvae can go through several pitchers, if not numerous plants. But something different occurs at the larvae's 5th instar, in which they will leave the pitcher they are actively consuming, go find a new pristine pitcher, but this time, instead of consuming the interior pitcher tissue, they will go to the very base of the new pitcher and chew a drainage hole, causing all of the pitcher fluid to expel. Once the fluid has expelled, the larvae will enter the empty pitcher to pupate, and then eventually emerge as an adult, starting this whole cycle over again of moths mating, larvae consuming plant tissue, and eventually causing pitcher desiccation. Now, because I use the plant as a model system, I know that desiccation is not only impacting the plant, but the organisms that I mentioned previously that inhabit Purpurea. Now, these organisms are fully aquatic, either in their larval stages, but for most of them their entire lives. So when pitcher desiccation occurs, we can assume death will follow shortly for these organisms. Historically, the literature on this system says that none of these organisms are capable of leaving the pitchers, but I wasn't convinced of this for one of these organisms, and that's Metronemus navi, our pitcher plant midge larvae. And I wasn't convinced of this based off of two pieces of literature. The first coming from Waines in 1972, who was studying the larval midge behavior, and they stated that at the fourth instar larvae, the midges frequently climb the pitcher walls up to and above the fluid level, but that this behavior does not appear to be associated with feeding or with pupation. About 10 years later, we have the researchers of Patterson and Cameron who are studying adult emergence rates of these midges, and they noted in their discussion that there was an occurrence of later instars in newly colonized leaves, indicating a migration of larvae from less suitable to more suitable habitat. So what they're saying here is that they found pitchers that had newly opened, and within these newly opened pitchers, there were these late instar midge larvae. Perhaps they emigrated to get there, but nobody's personally observed this, and nobody's conducted an experiment on this. So this leads me back to my original question of, are these midge larvae capable of emigration when pitchers become poor habitats, specifically in the form of desiccation, similar to the effects of the Xyrophax moth larvae? In regards to this question, I had three null hypotheses I was looking to test. The first being that the proportion of midge larvae surviving in place is the same for desiccated and undesiccated fluid-filled control pitchers. The second being that the proportion of midge larvae emigrating is the same for desiccated and undesiccated fluid-filled control pitchers. And then finally, that the proportion of midge larvae surviving in a new pitcher is the same for midges coming from desiccated and undesiccated control pitchers. So, to test these hypotheses, we conducted a small experiment where we used 15 plants, all of which were washed, rinsed, and then filled with RO water. The plants were randomly placed into two trays that were also filled with RO water and placed inside of insect tents outdoors. From there, 5 plants were randomly assigned to the category of low, 5 to the category of medium, and 5 to the category of high, and I'll come back to these categories in just a moment. From there, 1 pitcher per plant was designated as the experimental pitcher, and then once we had all of our plants set up, myself and my undergraduate researcher Sophie, pictured here, we headed out to Molly Bog in Stowe, Vermont, and collected larval midges. Midges were then transplanted into that one experimental pitcher for each plant. Previously, I mentioned those 3 categories of low, medium, and high, and this represents the abundance of midges that were going into that experimental pitchers. So our 5 plants deemed low received 2 larval midges in their experimental pitchers, our 5 plants deemed medium received 5 larval midges in their experimental pitchers, and our 5 plants deemed high received 10 larval midges in their experimental pitchers. We then allowed 4 days to go by for our midges to acclimate to their new home. And then at the end of 4 days, 4 out of the 5 plants for each category of low, medium, and high received a hole punch into the back base of that experimental pitcher, so in zone 5, using an 18-gauge needle, and this was done to mimic the hole size and placement created by the Xyrophax moth larvae, while the other experimental pitchers per category remained intact and served as controls. We then allowed the pitchers to drain of fluid and 2 weeks for the midge larvae to emigrate if they so chose. Then at the end of 2 weeks, I dissected the experimental pitchers, counted up all the midge larvae that were present, and noted their status of either living or dead, and then repeated this process for every other pitcher. So now that we went over our methods, let's go ahead and jump right into our results. So in this first figure, I'm showing the proportion of our initial abundance of midge larvae surviving in desiccated pitchers and in control pitchers at the end of 2 weeks. So here in the control pitchers, we found that 97% of our midge larvae were able to survive, while in our desiccated pitchers, only 11% of our midge larvae were able to survive. And even 11% was surprising to me, but these midges were actually able to crawl down so deep into the pitcher, there was still a little bit of moisture there. But with these results, we're able to reject our null hypothesis that the proportion of midge larvae surviving in place is the same for desiccated and control treatments. In the second figure, again I'm showing the proportion of our initial abundance of midge larvae now emigrating from desiccated pitchers and our control pitchers. So we did find that 3% of our midge larvae from our control pitchers actually did emigrate, while 50% of our midge larvae from our desiccated pitchers emigrated. Again, allowing us to reject our null hypothesis that the proportion of midge larvae emigrating is the same for desiccated and controlled treatments. In this final figure on the slide, I'm showing the proportion of our initial abundance of midge larvae, this time surviving in a new pitcher coming from either desiccated pitchers or control pitchers. So for midges coming from control pitchers, we found that 0% or none of our midges were able to survive in a new pitcher, while 25% of our midge larvae that emigrated from desiccated pitchers were able to survive in a new pitcher. Again, allowing us to reject our null hypothesis that the proportion of midge larvae surviving in new pitchers is the same coming from desiccated pitchers and control pitchers. Now, as I mentioned previously in methods, we had those varying initial abundances, and I was also interested in how initial abundance will impact survivorship within a new pitcher. So here on the x-axis, we have initial abundance, those three categories of low, medium, and high. And on the y-axis, we have our proportion of our initial abundance of midge larvae, this time surviving in a new pitcher. Now, although we did not see a difference in survivorship between our low and medium initial abundance, we did find that with a high initial abundance of midge larvae, there is an increase in survivorship within a new pitcher. And this makes sense to me. With pitcher desiccation, there's a rapid decline in resources, space, habitat overall, and so with so many individuals, it most likely pushes them up and out of the pitcher, or perhaps one midge simply left and the others followed. But in conclusion, we did find that midge larvae can emigrate successfully to a new pitcher, and that this historically closed system is not the case. As I just mentioned, we also found that a high abundance of midge larvae can increase survivorship in a new pitcher. I also wanted to note that there were some instances that larvae were unaccounted for, but I still noted them as emigrated. Most likely, I think they were present in the sphagnum moss that the plants were potted in. There were also instances that I found midge larvae present in the tray water. I think it's highly unlikely that I was just unable to identify them due to decomposition, as all of the dead larvae I found were still intact. I also wanted to bring up this idea of long-distance dispersal, or plant-to-plant dispersal, which for this experiment, I believe I did not observe. I would have expected to see a net gain in at least one plant, which I did not. However, I think in a more natural area, like a sphagnum bog, this is plausible, and that there's that moist medium for the midges to traverse over. As well, the plants are in much closer contact. They could even have pitchers touching. I will end this talk by discussing future research endeavors, the first of which will involve studying the physical morphology of the midges that are capable and incapable of emigration, as I believe it has a lot to do with the size of the posterior pro-leg hooks, which you can see here. I'm also interested in determining direction of emigration. Oftentimes, the Xyrophax moth larvae will cause girdling of the pitchers or have the pitchers collapse in on themselves, which makes movement through the top of the pitchers difficult. Midges are also photosensitive, so weaving through the drainage hole may be more advantageous for these midge larvae. Finally, work that I have recently started has been surveying the status of the Xyrophax moth larvae in bogs throughout Vermont. Currently, we're looking into presence-absence of these moths in these bogs, as well as how the moths are choosing plants to consume. But eventually we'll also be looking into how these moths are impacting the community structure within Sarracenia purpurea. And with that, I would like to end with just acknowledging some individuals. I would like to acknowledge my past committee members, as well as my advisor, Dr. Nicholas Gatelli, the Gatelli Lab as a whole, my undergraduate researcher who helped me with this work, Sophie, the University of Vermont for allowing us to collect larval midges in one of their natural areas, and then the University of Vermont's greenhouse for letting us conduct our experiment in their outside property. With that, happy World Carnivorous Plant Day.
It's not a surprise that gardeners, educators, and scientists are fascinated by these unique plants. The International Carnivorous Plant Society, or ICPS, not only love these plants, but welcomes growers just getting started all the way through professional scientists. The ICPS even started an annual World Carnivorous Plant Day to celebrate them. The free online event is held the first Wednesday of May. Take a look around our website and you'll find historic documents about carnivorous plants, growing guides, free educational resources, and more. Have questions? Ask. We don't bite, but our plants do.